be talking about solving a system by using what's called Gaussian elimination. And to get there, first we need to talk about what a matrix is. So a matrix is just a rectangular array of numbers. For example, this 3, -9, 4, 100, -2, 5, 1/2, 0 is a matrix. And it has 2 rows because there are 2 rows going across, and 4 columns. Columns go vertically. So we would say this is a 2 by 4 matrix. Well, when we talk about systems, one thing that we can do is rewrite the system in a matrix, removing the variables and just keeping the coefficients and the constants. So let me show you what I mean. Suppose we have this system. It is 2x plus y minus 3z equals -2, and x minus y plus 6z equals 5. And the third equation will be 3x plus 2y plus z equals 11. We can write what's called an augmented matrix by simply writing the coefficients of each of the variables in our matrix. So I would have 2, 1, -3, 1, -1, 6, and 3, 2, 1 over here in this matrix. But I also want to include the constants. And I'm going to draw this vertical line here to separate the constants from the coefficients and have -2, 5, 11. So this augmented matrix represents this particular equation. And of course, if we had an augmented matrix, we could go back to the system. For example, I could have this augmented matrix. It's 1, -1, 6, 5, 0, 1, -5, -4, and 0, 0, 1, 2. So here's my matrix. Let me write it as a system so you can see the variables and the equations. It would be x minus y plus 6z equals 5, and 0x plus y minus 5z equals -4, and 0x plus 0y plus z equals 2. Now notice this system is pretty nice to solve because you can easily do back substitution to find the solutions. For example, we already know the z-coordinate of the ordered triple, that the solution to this system is equal to 2. If we substitute 2 into the previous equation, we would have y minus 10 equals -4, or y equals 6. Let me just squeeze that in here. So far we know the z-coordinate is 2, the y-coordinate is 6, and we can substitute both of these values into the first equation, and we have x minus y, let me write the whole equation here, plus 6z equals 5, and then we'll do the substitution. We have x minus 6 plus 6 times 2 equals 5. Let's do the arithmetic there. We have -6 plus 12, that's 6. So we have x equals -1. So our ordered triple, that is the solution to this system, is -1, 6, 2. So notice it was very handy to have the equation looking like this because we could find the solution easily by doing back substitution. And it turns out that these two equations or two systems that I gave you are equivalent. This solution right here is actually the solution to this system as well. So our task for Gaussian elimination is going to be, how do we take a matrix that looks like this and transform it into a matrix that looks like this so that we can easily state the solutions. And that process of transforming the matrix from this to this is the process of Gaussian elimination. So our goal is to be able to write a matrix in this form. Well, what does this form mean? It's actually called row echelon form. Our goal is going to be to write our augmented matrix in row echelon form. And let me tell you the things that are required for it to be in row echelon form. There are 3 things that are required, and you can see I've listed them here. A matrix is in row echelon form if the first non-zero number in each row is 1, and that non-zero entry is called the leading entry. The leading entry in each row is to the right of the leading entry in the row immediately below it, or above it. And if you have a row of zeros, we did not in the previous example, it needs to be put at the bottom of the matrix. We're not going to do one that looks like this today, but just know that if you had a row of all zeros, they'd need to be at the bottom. So let me show you with the system or the matrix that we just had, how that meets that criteria. Notice the first non-zero entry in each row was a 1. Here's our leading entry, here was our leading entry, here was our leading entry, they were all 1s. And this 1 is to the right of this one, and this one was to the right of this one. So now the question is, how do we transform a matrix that looks like this into a matrix that is in row echelon form? So I have a list of the steps that we can use. They're called our elementary row operations. And let me list them and then we'll talk about them. Our elementary row operations are these, and there are just 3. You can interchange any 2 rows you like. You can multiply a row by any non-zero constant. You can't multiply by 0 because you'd wipe out the equation essentially. And you can add a multiple of one row to another. These are the things that we're going to do to transform a matrix into row echelon form. Now let me address each of them. Let's start with interchanging 2 rows because I want you to see why these are valid. If you had a system like this, for example, 3x plus y equals 11 and 7x minus 2y equals 14. We know that switching the order of those equations would not in any way change the solution. It doesn't change the place where those 2 lines would intersect. Similarly, changing the rows in a matrix wouldn't have any effect on the solution. So interchanging the rows we can do, and pretty easily. The next is that we can multiply by a non-zero constant. So again, if we think in terms of systems that we have solved before, if you were going to solve 1/2 x plus 3y equals 10 and 4x minus y equals 17, for example, maybe you didn't want to work with fractions. Perhaps you would just choose to multiply this equation by 2. It's our multiplication property of equality that we use all the time in algebra that says if you have an equation, it's totally okay to multiply an equation by a constant. So we'd have x plus 6y equals 20 and 4x minus y equals 17. And this system is considered equivalent to this one. That means they would have the same solution. So similarly, when we're working with matrices and we're using our elementary row operations, if we see a matrix and we see a row that looks like this, 1/2, 3, and 10, I'm just popping these numbers into our matrix. If these numbers represented this system, it would be totally okay to multiply that row by 2 and have this as our new matrix. It's one of our elementary row operations. And let me address the third and final elementary row operation. That is multiplying a row by a number and adding it to another row. We do that all the time as well. Let me come back to this system. Suppose you were going to solve this system using elimination. You could multiply this equation right here by 2 and create this system. 7x minus 2y equals 14 and 6x plus 2y equals 22. And then add those two together. We do this all the time when we're solving using elimination. It's a totally valid step when solving systems. And then you would keep going. But the idea is multiplying an equation by a number and adding it to another equation is a completely valid step when solving the system. So now let's put those ideas together and see how we would solve a system using Gaussian elimination. So here's the system we'll solve. It's actually the one I wrote up first. And we're going to get to that matrix that I wrote in row echelon form. But now we're going to see the steps that it takes to get there. So your first step is to write the equation, or excuse me, the system as an augmented matrix. And I'm going to put the brace on here so we know those go together. So my augmented matrix looks like this. 2, 1, negative 3, negative 2. 1, negative 1, 6, 5. 3, 2, 1, 11. And take care when you're doing that. It is super easy to make a mistake. Just leave off a sign. I usually double check, make sure my numbers are correct before I jump in. And now we're going to be very systematic about transforming this into a matrix that's in row echelon form. Remember, the goal is to have a 1 here and zeros beneath, and then a 1 here and zeros beneath, and then a 1 here. And we're going to do those things in the order that I just stated them. On many steps, you have a variety of things that you could do. Like right here, our first step is going to make this entry become a 1. A variety of things that we could do. We could just divide this row by 2. That's equivalent to multiplying by a half, and multiplying by any non-zero number is totally valid. But that would be introducing fractions into it, and although I could do it, there's something that would be a little bit easier. Another option would be to subtract row 1, or subtract row 2 from row 1. So if we subtracted 2 minus 1 and replaced row 1 with that result, we would have a 1 right here. But again, although doable, that's probably not the easiest. The easiest would be the first item that is listed on elementary row operations, and that is interchange any 2 rows. So I'm going to do that. Switch these two. And I'm going to write a road map along the way on the steps that we're doing. It makes it much easier to follow, and if you make a mistake, you want to go back and see what you're doing, I would encourage you to do the same. So we're switching row 1 and row 2. So row 1 and row 2 are switching spots. So it looks like this. 1, negative 1, 6, 5. Now this becomes row 2. 2, 1, negative 3, negative 2. And row 3 is unchanged. 3, 2, 1, 11. So I've taken care of the 1 here. My next step is to get a 0 beneath. Now the benefit of having this 1 here is it's easy to multiply it by a constant and add it to that row so that you can easily get a 0. In other words, if I multiply row 1 by -2 and add it to row 2, I will get a 0 there. So let me write the elementary row operation that we're doing. We're going to do -2 times row 1, add it to row 2, and put it in row 2. Mathematically speaking, let me mention this with respect to your elementary row operations. If you're doing a combination of row 1 and row 2, you can actually replace either row 1 or row 2. If you combine row 2 and row 3, you can put the result in row 2 or row 3. What you can't do is if you're using row 1 and row 2, you can't put the result in row 3, for example. But let's go. Let's do this arithmetic. So here we are. We're multiplying this row by -2 and adding. Now, you get better at doing this as you practice. I'm going to show you just doing it in our head, and then I'll show you, we'll do it on paper as well. So multiply -2 times 1 is -2, and add 2. That's a 0. And let me write down row 1 because it is going to be unchanged. And I'm back over here. I'm multiplying by -2 and adding. So -2 times -1 is 2, plus 1 is 3. -2 times 6 is -12, plus -3 is -15. -2 times 5 is -10, plus -2 is -12. And if that's hard for you to see, grab a piece of scratch paper. I'll grab my scratch paper. Right? And you can do the arithmetic here. I have the -1, -1, 6, 5, and the 2, 1, -3, -2. I am multiplying this row by -2, and I'm adding it to this one. So I would have -2, 2, -12, -10, and 2, 1, -3, -2, and add. And notice that's a 0, 3, -15, and -12 that I wrote right here. Nothing wrong with grabbing a piece of scratch paper if you need to see it, but also nothing wrong with practicing and doing it in your head as I did right here. Either way is totally fine. Let's do our next one. Oh, I need to finish this row. 3, 2, 1, and our 11. So we have our 1 and our 0 beneath. We need a 0 here. We're going to multiply row 1 by -3, and we're going to add it to row 3. So let me jot that down. It's -3 times row 1 plus row 3, and we're going to put it in row 3. So if you want the scratch paper back, let's do it. Here I'm talking about row 1 and row 3. Here's row 1 again. And here's row 3. And this time we're multiplying row 1 by -3, and we're going to add it. So let's see, when we multiply it by -3, we have -3, 3, -18, and -15. And we're going to add that to 3, 2, 1, 11. And we get, excuse me, 0, 5, -17, and -4. So that's what we're going to place in row 3. So here's our matrix. Row 1 is unchanged. Row 2 is unchanged. And now our row 3, here's my scratch paper. We have 0, 5, -17, and -4. And now we continue. We have finished this column. 1 and 0 is beneath. Our next step is to get a 1 right here. And notice I can easily divide by 3, which is equivalent to multiplying by 1/3. So that's nice to do for our next step. We're getting a 1 right here. So we're multiplying 1/3 by row 2, and we're putting it in row 2. So now our matrix looks like this. 1, -1, 6, 5. 0, now we're multiplying by 1/3 or dividing by 3. 1, divide by 3, -5, -4, and our row 3 is unchanged. And we're getting closer. Our next step is to get a 0 right here. Now I do want to let you know that we don't want to involve this first row in the calculation. Sometimes people want to multiply row 1 by 5 and add, and while that would give you a 0 here, we would lose this 0 here. It would no longer be 0. So use row 2 with row 3 in order to make that be a 0. So let's see. We're going to multiply row 2 by -5 and add it to row 3. So let's write that down. -5 times row 2. We're going to add that to row 3, and we're going to put it in row 3. So row 1 is unchanged. 1, -1, 6, 5. Row 2 is actually unchanged as well. 0, 1, -5, -4. And now we're going to find our new row 3. You can grab a piece of scratch paper to do it, but let's just do it mentally right here. We're multiplying by -5 and adding. Let's see if we can do it. -5 times 0 plus 0 gives me 0. -5 times 1 is -5, plus 5 is 0. If that hadn't been a 0, I know I made a mistake. -5 times -5 is positive 25, plus -17 is 8. And -5 times -4 is 20, plus -4 is 16. Now, if that bugs you, just grab a piece of scratch paper like I did on the previous two to find those values. And I hope you can see our last step. We need to make this be a 1. For it to be in row echelon form, we need 1s along this main diagonal. So our last step to get it in row echelon form is to divide by 8 or multiply by 1/8. So we're going to multiply row 3 by 1/8, and we're going to put it in row 3. So our matrix looks like this. 1, -1, 6, 5, 0, 1, -5, -4, and 0, 0, 1, 2. And now we have the matrix in row echelon form. Once we get here, we know it's a matter of back substitution to find our solutions. We have x minus y plus 6z equals 5. We have y minus 5z equals -4. We have z equals 2. And this is the system that we solved a few minutes ago. Here it is, right? So to finish, you would substitute 2 in to the previous equation and find your value of 6, and back substitute again and find your x value of -1. So I'm not going to repeat that because we already did it, but we would find that our solution is -1, 6, 2. And we have solved our system using Gaussian elimination. Now let's recap the steps. here's what we do in solving a system using Gaussian elimination. Write the augmented matrix of the system. Use your elementary row operations to change the augmented matrix to row echelon form, and that's where most of the work is. That was all of this that we did. And then use back substitution to finish solving the system. So you take your z value, substitute it into the previous equation and find y, and then take your y and your z and substitute it into the first equation and find x. I hope that you practice some Gaussian elimination problems. It does take some practice to really get down the elementary row operations. And in my next video, I'll give you a few practice problems.